Um, so we started off with this, the basis of electrolysis, what are conductors, what are insulators. We have examples over here. How do we commonly supply electricity all around the world? What kind of materials or metals do we use? What if there are some liquids that can conduct electricity? We have separate name for them, electrolytes and non-electrolytes. It works like the same thing. We have examples of them over here. Then we moved on to the basics of how conductivity happens, how the ions move during electrolysis. We had a simple, colorful experiment to show you that, which explained the basics of electrolysis itself, the electrode, cathode, anode, cations, anions, the two kinds of ions that are included in this portion. Then we discussed the working of a simple electrolysis cell, then started the electrolysis of molten compounds. Now, we did electrolysis of the molten compounds. There are a few examples in the book. Zinc chloride is there, lead bromide is there, some basics are there. These all the pink portions in this chapter are very, very important. You can't leave even a single one out of it. And finally, the electrolysis table for molten compounds. Now, in between these parts, what you're going to see is that you're going to see industrial electrolysis. For molten compounds, there is an industrial electrolysis present on page number 107. And then it continues next. This is actually aluminum oxide, for which they discuss the industrial electrolysis. Then starts electrolysis of solutions. We're going to do this industrial electrolysis today. Then starts electrolysis of solutions. They discuss that we've already discussed what happens at cathode, what happens at anode, all of that. Then for industrial electrolysis, we have electrolysis of concentrated sodium chloride solution. We have this diagram we need to discuss. What happens if we do it in industry? There is a separate industrial diagram over here for the same cell electrolysis. Moving on, electrolysis of acid solutions, which we really call electrolysis of water, for which we have a diagram 4.26 at the bottom of page 111. And this, from here on, we have electroplating started. Electroplating is really a very small topic, and it really covers in just one page. Then we have electrolysis tables for aqueous solutions, solved, unsolved, both kinds of tables. Special cases like concentrated hydrochloric acid and dilute hydrochloric acid. Then at the end of the chapter, we have a very small portion of refining of copper by electrolysis. This is also industrial. So refining of copper, aluminum oxide, sodium chloride, dilute acid solutions or water. These are the industrial parts, including electroplating, that we need to discuss today. So these are 4 to 5 very small topics which I am going to cover today, uh, putting them all into one place. So I'm back to page 107, the heading Industrial Electrolysis of Molten Compounds. Now, since this topic is covered in two different parts of the book, one over here in chapter number 4, uh, one part is covered in chapter number 8. So I'm going to connect both so that I can show you the interlinking of both the chapters, discuss all the details at once. And we're not going to go through the same topic in chapter number 8. We're simply going to skim through it. All right. So let's quickly get to that. Electrolysis is important industrially. It is one of the only methods of extraction for reactive metals. This includes metals in group 1, group 2. To be honest, we're talking about the upper part of the reactivity series. If you've tried to remember it with the mnemonics I told you about, or your mnemonics of your own, whatever that is, we are back to Kanaka Magalsi. So uh, this is what we had on top. Now, before carbon, these were the 5 most reactive elements in the reactivity series. It includes elements in group 1, group 2, aluminum, all of these. Now, they have to be extracted by electrolysis process because we cannot use reduction with carbon. Carbon is less reactive than these. So carbon cannot go with for a displacement reaction with these. So that's not possible. So the only option we have is really electrolysis at this level, at least. So what do we do? When we come to aluminum and we discuss aluminum, we are bound to go with electrolysis. Now, one of the most important discoveries in the industrial electrolysis was finding suitable conditions for extracting aluminum from its mineral ore, bauxite, and to then produce molten aluminum from it. Now, there are some things or information pieces of information that are given over here, but this topic is discussed in much more detail in chapter number 8. So we're going to directly jump to chapter number 8. Let's jump to the extraction of aluminum. Sorry, it's not chapter number 8, my bad, it's chapter number 9. There you go. 9.2, the extraction of metals by electrolysis. This tells you for most of the metals, at least for aluminum, which we're going to discuss over here, the three simple steps are we mine the ore from the earth. The ore over here is bauxite. Bauxite is mainly Al2O3, but in the earth's crust, it is present in the form of Al2O3.2H2O. So we mine it, then we purify it, and then we move on to its electrolysis. So bauxite, if I go to the bottom of this page, and let me tell you, this is page number 234. Okay, so extraction of aluminum, bauxite, main ore, a little bit of history. Let's not go towards that. Its picture, it's really not red brown. It's red brown due to the iron 3 oxide present. Bauxite is not red brown. Okay, so moving on. It's a Hall-Héroult process, the electrolytic method by which we actually go for the electrolysis of aluminum compounds. Hall, American chemist, Héroult, Frenchman. Now that's why it's called known as Hall-Héroult process. Now in some old books, you might see this name starting with a B, Hall-Héroult process. Doesn't matter. It's just a way of writing the name. Since it's a foreign name and not an English name, of course, it's French. So it can be written with different techniques. So don't worry about that. Let's get started with the process. We are not interested in history. And as you know, IGCSE and O level never asked about the history or the scientist names. So let's not really get into that kind of detail. Okay, so bauxite is an impure form of aluminum oxide. Up to 25% of bauxite consists of impurities or like iron 3 oxide and sand and other kind of stuff. So we need to first purify it a little bit. All right. Iron 3 oxide is the one which gives it a red brown color, which I just showed you at the bottom of page 234. Now, Hall-Héroult process involves the following stages. The first stage really is the purification stage. We haven't started electrolysis at this stage, so we can safely say point number one is related to purification. And it's the same point that we discussed over here, so it's the same over here. What do? We take sodium hydroxide, the formula for which is NaOH, and we treat bauxite with it. It gives us pure aluminum oxide, or which we also call alumina. All right. So that's how we get rid of all the impurities, be it sand, be it iron 3 hydroxide, or iron 3 oxide,
Sir,
whatever. G.
I got disconnected.
We just started off the process. There isn't much of the stuff that you missed. All right.
Okay, sir.
Since you're supposed to start with this heading, anything before is really history, and history is not asked in exams, so don't worry. The first step is purification. And what do? We treat with NaOH. Treating with NaOH gives us pure alumina or aluminum oxide, both names. Alumina is common name, aluminum oxide is the actual name. And this is then shipped to electrolysis plant. So we leave everything like iron 3 oxide, like sand, any of the impurities behind. This was what I just discussed. Let's continue with where we were going. So point two is basically electrolysis. Now, purified aluminum oxide is dissolved in molten cryolite. The name of the actual name of cryolite is sodium aluminum fluoride. The formula is Na3AlF6. Cryolite is important over here. And if you're going to take a look at the past papers, you're going to find many questions about cryolite. Cryolite was a mineral that was naturally found in Greenland, but it is no longer mined commercially there. And all the cryolite in the Earth's crust has been used so far as we know, and cryolite is now made synthetically. So Cryolite is actually used to lower the working temperature of electrolytic cell. Let me tell you the two purposes of cryolite. Number one, cryolite acts as a solvent. How do you know it acts as a solvent? Clearly, aluminum oxide is dissolved in molten cryolite. So aluminum oxide is solute, cryolite is solvent. It's stated right there in his book, but it's written in such a way that students sometimes are not able to come up with this explanation. So straightforward is that I've told you the explanation, the first function. The second function really is to act as an impurity. And before I move any further, let me clarify. Chapter number 2, the very start of chapter number 2, 2.1 tells you if there is an impurity in a solvent, it can decrease its melting point and increase its boiling point. So if cryolite is present with aluminum oxide as an impurity, what would happen? It decreases the melting point of Al2O3. That's the second function. Commonly, past paper questions ask us the two different functions of cryolite. There you go. You have both of them. Make sure you note it down because these two are not written in the similar way in the book. This is the smallest sort of answer, and you can straightforwardly put that answer in the questions and get 2 marks, for which the usually question stands for. Now, if we're going to add cryolite, the working temperature of the electrolytic cell, which should be around the melting point of aluminum oxide, and having said, a melting point of aluminum oxide is 2030 degrees centigrade. Now, using an impurity benefits us a lot. It is reduced to around 900 to 1000 degrees centigrade. Now, that's great. Imagine to get to this melting point, we must have to burn a lot of fuel. That fuel will produce fire, that fire will increase the temperature and will be used to melt it. Imagine if we half that temperature, or even if we use less than the half of this temperature, 900 to 1000, around 900 is definitely less than half of it. Imagine we can save a lot of cost in fuel. And the same thing is written in the next line. The cryolite thus provides a considerable saving in energy cost. Fuel is expensive. Name a fuel, be it coal we are using, be it diesel, be it any other kind of fuel. Definitely, you're not going to burn petrol. Petrol is really very expensive when it comes to a comparison of coal and diesel, but still, you were going to burn some fuel. And lowering the temperature to its half is definitely going to save a lot of amount of any fuel you were using. So the third point reduces cost. It doesn't exactly reduces cost directly, but definitely indirectly. Because when it acts as a solvent, it lowers the melting point, or when it acts as impurity, it lowers the melting point and thus reduces our cost. I hope you get the point. Do you? If you're both clear, we can move forward.
Yes, sir.
Yes,
Okay,
sir. Yes.
good, good. Let's move forward. Now, since we're ready to actually go for electrolysis, the molten mixture is then electrolyzed. This is the diagram of the electrolysis, and some very important equations are written right over here. Now, we are already done with these equations in our electrolysis table, and I'm going to show you once we get over there, is that aluminum ions gain 3 electrons and are converted into molten aluminum. Oxide ions are going to lose electrons to form oxygen. This happens at anode, this happens at cathode. So we are producing molten aluminum as cathode, we're producing oxygen gas at anode. Now let's take a look at the structure. This entire structure has major parts as cathode. There we have a carbon cathode. Let me tell you, the word carbon is written over there. We are probably talking about the graphite. Graphite is a form of carbon. So graphite cathode, then there is some insulation. On the top of it, we collect our liquid aluminum, and then there are heavier anodes, and we have alumina hopper, from which we add more and more alumina, all right? Because at one point, we are going to consume all of alumina, so we add more alumina to it, okay? So that's the hood, which is usually made up of steel. Molten electrolyte consists of alumina plus cryolite, of course, and we have a steel shell outside, we have carbon block lining. This is the whole structure. They're not going to ask you questions about this kind of stuff. They usually don't. They might ask you about the electrode, about where do you get liquid aluminum, these anodes, of course, and these equations are very important. They have been asked a number of times in the past papers. Okay. And you're not going to find both of the equations in the written text. I'm going to move forward. You're going to see that you would only find the equation of aluminum. You won't find equation of oxygen over here. So oxide ions are converted into oxygen gas. So liquid aluminum is catered at cathode. Oxide ions are attracted to anode where they discharge in the form of oxygen gas. They actually try to bubble out of the liquid or the molten system. At this high temperature, when that happens, oxygen actually the oxygen that forms reacts with the carbon of cathode. Now, cathode was made up of graphite. So graphite anode, my bad. I have written the wrong electrode. Let's correct it. So graphite anode actually reacts with oxygen and gives us carbon dioxide. So we say that anodes burn away. And literally that happens slowly. एनोड्स आहिस्ता आहिस्ता जलते रहते हैं, ऑक्सीजन प्रोड्यूस होती रहती है, एनोड्स बर्न होते रहते हैं. And at the start of the reaction, we may start with a very good strong anode, and by the end of it, we might have all of the anode burned and just the upper part left. All right. So we regularly replace anodes. Now the good part is graphite is cheap. We can keep replacing the anodes. That adds to the cost of aluminum, of course, but not that much. Hall Héroult process uses a great deal of energy. Why? It is using electrical energy. Electricity is expensive. So it's costly to replace the anode, which burns away during the process. It's much cheaper to recycle the material than to manufacture. He's now talking in comparison, right? So the energy requirement for recycling is about 5% than manufacturing the same amount of new material. So recycling of aluminum is a great idea. Imagine we can save 95% of the cost if we recycle aluminum, right? Okay, moving on. That's about it for the process. I hope you're clear. And we are going to get back to chapter number 4. All right. So the same pieces of information are present over here. The bauxite treated first, molten cryolite, much lower temperature, electrolyze, the equations on cathode and anode, simpler diagram for understanding what actually happens with it. And finally, operating temperature about 1000, graphite anodes burn away. We need to replace them regularly. All the pieces of information are also present over here. So that's just a repetition. And that actually completes the industrial electrolytes of molten material. Any questions so far?
No,
Okay, good.
sir.
Don't have any questions. Let's move on to electrolysis of solutions. The first industry we have is concentrated sodium chloride solution. Now, concentrated sodium chloride solution is also named as brine solution. Brine was the name of the scientist who first electrolyzed this solution. ठीक है, वैसे तो हम मजाक में कह देते हैं concentrated sodium chloride is actually the table salt we eat every day. So concentrated sodium chloride solution सिर्फ नमक वाला पानी है, तो साइंटिस्ट ने कोई खास काम नहीं किया है. But yeah, Brian actually electrolyzed it or tried to electrolyze it at least. So yeah, that's a big name. Just because ये नमक वाला पानी है, you can't actually take that name for a joke, which you may find as a meme over the internet. Okay, so there are 4 different ions present in the system. We are done with that practice yesterday. There are sodium positive ions and chloride negative ions coming from the salt. There are H positive ions and OH negative ions coming from water. And this is the kind of electrolysis that we usually do. Now, this is for the lab. This is not for the industry. Okay. And this diagram is equally important for paper 2 MCQs, for paper 4 theory, and for paper 6 ATP. Now, let me give you some shocking news. In ATP, they have asked this specific diagram as a part of the question to draw the diagram. Now, whenever you're going to perform an electrolysis in lab for which the result is a gas at anode and another gas at cathode, you're always going to do it in inverted test tubes. Like you can see in front of yourself, there is a tank. In the tank, we have straight up electrodes. The anode, this is the anode, this side is the cathode. Of course, how do we know? Because negative side is always considered as cathode from the power supply and positive side of the power supply is anode, right? So on these electrodes, we're going to invert the test tubes. What happens then is that liquid rises a little bit, but as soon as we have gases collected over here, those gases are going to stay over here. They're not going to escape in the environment, which actually keeps everything safe. Now there we have no hazards with hydrogen apart from fire hazards. I mean, a toxicity hazards are not there, but fire hazard is definitely there. Hydrogen is very much flammable, can very easily catch fire and burn explosively. In terms of chlorine, it's actually a toxicity hazard. Chlorine is poisonous, to be straightforward. So if you're going to interact with it, this is going to be a big problem. So carrying out this experiment is usually just a teacher's demonstration. And even that, we do it either in a fume cupboard, the whole thing is covered inside a cupboard so that gas is never comes out to the environment. Or if you don't have fume cupboard in the school lab, we do it in a well ventilated space. Make sure to turn on the fans, exhaust, open the windows, everything so that you don't have to interact with chlorine. Because the chlorine's effect is really instantaneous. You start coughing right there, you have problems, runny nose, teary eyes, and difficult to breathe. Everything starts with chlorine. So yeah, all of these information is specifically for paper 6. They usually don't ask these kind of questions in paper 2 or 4, neither MCQ nor theory, usually. Okay, so the electrolysis cell is fitted with graphite electrodes. And of course, at cathode, these two ions are going to compete. At anode, these two ions are going to compete. This is a concentrated sodium chloride solution. If the word concentrated is written before it, it definitely means it's concentrated. But even if the word is not written with the solution, the standard understanding for any solution for electrolysis without any details for the dilute or concentrated means it's automatically considered as concentrated. All right. If they do not mention the word concentrated or dilute before the solution, you are going to consider it concentrated. Okay.
Okay,
So
sir.
moving on. Since we are done with this whole thing, you know, hydrogen is less reactive. So this goes to the electrode and forms hydrogen gas. Chlorine is present in higher concentration. This chloride ions are present in higher concentration, so they form chlorine gas. We're left with sodium, we're left with hydroxide. And I hope you remember from the last class that these two are going to react and they're going to form sodium hydroxide solution for us in the aqueous form, of course, since there is water over here. Now, I hope you remember this all since that's going to be a part of the next page, hydrogen form hydrogen gas, we write it like this. This is the final equation that you're supposed to mention in exams. You're not supposed to mention this or this. This is for your understanding only. Again, this is for your understanding. This is for your understanding. You're not going to mention these equations. And this is the final equation you mention in exams. Okay. Don't forget the observation part that hydrogen is a colorless gas. So we are going to see colorless bubbles over there. On the other hand, chlorine is a pale green gas. So we're going to see pale green gas bubbles over here. And you're going to exactly see that thing in this diagram. Take a look. Hydrogen has been drawn white. chlorine has been drawn with a pale green color for labs as well as for industry. There are colorless bubbles for hydrogen. There are pale green bubbles for chlorine. So this kind of information really depends upon your memorization capabilities, since you are going to remember that hydrogen is a colorless gas and chlorine is a pale green gas. And I am clearly stating that it's a memorization part. There is no understanding about it. These are just facts. You're supposed to memorize them. Left behind in the solution are NaO positive and OH negative. Since I've already explained, they form sodium hydroxide solution. So our products are hydrogen, chlorine, and sodium hydroxide. And they're very important in industry. All of them have very important uses, which have been given in chapter number 9. This part is also explained in chapter number 9. Let's connect it. I'm not going to reteach it once we get to chapter number 9. Okay, so 9.2 was all about electrolysis of uh, aluminum oxide, bauxite. If you move a little bit further, you are going to find it as a topic over here, 9.5, the chloralkali industry. Now, the word chlor actually is representing chlorine that we get from this industry. Alkali is representing NaOH that we get from this industry. The solution is named as brine. There are different types of cells that we have. Mercury cathode cell, old information, not a part of course anymore. Diaphragm cell, old information, not a part of course anymore. All right, you can simply skip these parts. These are old pieces of information. They're not even present in the next edition of the book. They're present in the next edition of the book, just not in the form of separate paragraphs, bullet points, not that important, just in a couple of lines. The important part is membrane cell. This is the most modern system. This is the selective ion exchange membrane, and it keeps the products apart. We are going to see this back on page 110, which we were previously studying. What I wanted you to see is that we have three products from electrolysis of brine. Chlorine, there you have its uses. Sodium hydroxide, their uses. Hydrogen, their uses. Since uses are not a part of chapter 4, that's why we do not discuss it over here. So I'm not going to teach you uses, and just was referring to it since they're literally a part of chapter number 9 and never asked in parts of chapter 4. So I am back to the same page, page number 110 finally. Industrial electrolysis. So industrial electrolysis is known as membrane cell. It has a titanium anode and a nickel cathode, something you need to memorize. Titanium is chosen for anode because it is not attacked by chlorine. And again, nickel is chosen as a cathode because hydrogen does not react with nickel. So anode and cathode compartments are separate, and they're separated by a membrane, just like the membranes we have discussed in biology. Then the membranes are selective. The word selective means partially permeable. Now, this term actually comes from biology. Partially permeable is selective. This means this does not allow all the ions to pass. This does not stop all the ions. It's actually selective. How is it selective? It's going to let sodium ions pass through the membrane. It's going to let water pass through the membrane, but no other ions can pass, which means we're specifically stopping these ions. Let's go through the diagram to understand this fact, and you can see it right over here. Now, the brine is coming from one side. This is the anode compartment. This is the cathode compartment. And here we have a tap that gives us out the sodium hydroxide solution. Hydrogen, since that's a gas, it rises up top on the cathode compartment. Chlorine, again, a gas, rises up top on the anode compartment. Titanium anode, nickel cathode. And this in the center is your ion exchange membrane. Now, this ion exchange membrane is allowing the sodium ions to pass through, but they never allow chloride ions to pass through. That's the best part of it. And water is, of course, flowing through over here. So chloride ions stay in this portion, and we get almost pure chlorine over here. Almost. I'm not saying exactly pure. Okay. And we get hydrogen over here. Since OH ions stay over here. Most of the water is over here. And sodium ions can also pass over here. So we keep getting sodium hydroxide ions out in the form of sodium hydroxide. That's the way we perform it in the industry. We get all three products from here, and that completes the electrolysis of concentrated sodium chloride or electrolysis of brine solution. Any questions from this part?
No, sir.
Moving on, electrolysis of acid solutions, or I would rather write it as electrolysis of water. Since past papers have asked this question as electrolysis of water most commonly. Now, the instrument that we use really over here is known as Hoffman's voltmeter. And so since we're decomposing water and water is made up of H positive and OH negative ions, you really get those H positive ions at cathode and they give form hydrogen. You get those OH negative ions at anode and they form oxygen. Pretty much understandable. Water is made up of hydrogen and oxygen. And when we break down water with the help of electricity, electrolysis of water, it gives away hydrogen and oxygen again. Let's go to the diagram to understand the further basics of it, right? So this is Hoffman's voltmeter. Again, you can see the electrodes at the bottom of it, and we have the huge compartments there. We keep adding water from here, all right? And these are tapped. Oxygen gets collected over here, hydrogen gets collected over here. We add a little bit of dilute sulfuric acid to make the whole water as electrolyte. Remember, pure water is not a good electrolyte. Pure water cannot conduct electricity as good as mineral water or salty water does. So what do? We can either add a little bit of salt to this water. We can even add a little bit of acid to this water. Adding a little bit of the strong acid to this water really works well. We have platinum electrodes and we keep producing these gases. Now, let's get to the past paper question, something that have been asked in past papers way too many times. Now, take a look at the volume of oxygen, sorry. Oxygen is this much. And take a look at volume of hydrogen, it's this much. So literally, hydrogen gas is almost double than that of oxygen gas. Why is that? The explanation is pretty simple. Since water is composed with two molecules of hydrogen and one molecule of oxygen, so when we decompose it, we get double the amount of hydrogen and as compared to oxygen. It's pretty simple. So this is the ratio of hydrogen and oxygen atoms in its formula of water, and this is the ratio of hydrogen and oxygen gases that we get over here. All right? Understandable?
Yes,
Good. Actually, this completes electrolysis of aqueous solutions as well. Next part we have is electroplating. Let's move on to electroplating. All right, so what is electroplating? Electroplating is the fact that we do not consider cathodes. Now, so far, we have been taking cathodes that are made up of graphite or mostly platinum. Now, there was one example of the previous electrolysis of brine where it was either made up of titanium or nickel, but mostly graphite and platinum. What happens if we don't use these? What happens if we use the metal to form our electrodes for the same metal whose solution is inside there? For example, if we are electrolyzing, let's say we are electrolyzing copper chloride, and we use copper electrodes, what happens then? So electroplating is all about that. Instead of using these, we use actual metal electrodes. What happens then? So electroplating in that case actually coats one metal with another. You might have noticed that we have been discussing plating of different stuff. I'm going to give you literal examples from everyday life, and then you're going to get the idea. The most commonly used metals for electroplating, and afterwards I'm going to explain the chemistry of electroplating. So let's go with the examples first, since this is going to make you more familiar with the topic before I actually start with its chemistry. Now, the most commonly used metals for electroplating are copper, chromium, silver, tin. One purpose of electroplating is to give a protective coating. For example, tin plating of steel cans prevent them from rusting. That's why you have tin cans around the world for different beverages or for different fruit storages. For example, your Coke, Sprite, Fanta, name the most famous beverages around the world, you do find them in tin cans. Now, that can is actually made up of steel, but there is a very thin plating. That can is made up of steel, but there is a thin tin plating outside and inside. It keeps uh, steel from rusting. Since there is acid inside, there is water inside, it can easily attack steel and rust it, corrode it, invert into its oxides or hydroxides, but tin prevents it. Same goes for silver, since this is very unreactive. Remember, silver was present at the bottom of the reactivity series. And again, I am going to draw the reactivity series for you, the whole thing, so you get an idea what I'm talking about. Okay, this is the reactivity series. Now take a look. Steel is made up of iron, right? So this one is moderately reactive. If we use any element below it to cover it, let's say we are using copper, copper is present below it, it's less reactive. If you're using chromium, chromium is not in the list, so I'm going to skip that one. Silver is right below copper. We also use tin, tin is right below iron. Anything over here is actually less reactive, and if it's safe to put our eatables and drinkables, that's actually good. Lead is not safe, so we do not commonly use lead. We can use gold and platinum, but again, they're extremely expensive. Though they are the least reactive ones and the best ones for that kind of work, they don't get rusted at all, but they're very expensive. All right. Now, chromium plating. Chromium do not rust. Is usually done at car bumpers, kettles, bath taps. There are many examples. The shiny silver gray metal appearance is usually shown with chromium. What happens? Chromium does not corrode. It's a hard metal. It resists scratching. It resists wear and tear. It can be polished to give an attractive finish. Again, a lot of money. Car bumpers are made out with chromium so that they become really shiny and attractive to people. That's why car bumpers, when they have shiny silver appearance, because the chromium has been polished above it, is really attractive. I think Avais can tell it. If you're into cars, you would definitely know. Now, that's not it. The topic goes on. We electroplate silver on some cheaper stuff. We can see it on top of cutlery, the forks and the knives, the spoons that we use. They don't rust no matter what kind of water we put on them, what kind of acidic stuff we put on them. They don't rust usually. Nickel silver, electroplated nickel silver is a common alloy that we use all the time. Apart from that, gold plating is something which is pretty common around the world. Now, previously, gold plating was just a part of jewelry, right? So what do we do? We were used to make simpler jewelry out of copper or some other material, and we used to electroplate them. Now, let's suppose there is a ring, right? There is a ring that is made out of copper. If we're going to dip it in a solution of the whole electroplating material, which I'm going to discuss a little later, we can actually plate a very thin layer of gold on top of it, so it would be gold plated. It won't be made out of gold completely, so it's not going to be expensive, but at least the outer finish would be of gold. So we definitely can get a good price even when it's not. That's how artificial jewelry is made. Artificial jewelry is just gold plated. Now, gold plating is not just limited to jewelry. Now, you might have seen wristwatches gold plated. The most expensive cell phones are now gold plated or platinum plated, even. And then we have cars that are gold plated. Those are specifically made for the richest people on the planet. So I hope you know examples here and there over the internet or from the news. So what exactly is electroplating? How do we plate a wristwatch, or how do we plate a cutlery item, or how do we plate an entire car with gold or something like that? As you can see the diagram, there are specific electrodes that he's going to dip inside a solution of metal objects, and the rules are very basic. This whole thing is going to make you understand what we are about to do. Now, if you need to electroplate an object with a specific metal, and let's call it M, this metal can be chromium, this can be silver, this can be gold, it's entirely up to you. The object must be made the cathode. So we have that whole electrolyte system. Now, that object is made cathode. Let's say it's just a wristwatch. Okay. So we're going to make that wristwatch as cathode. Let's connect it to the battery. I shouldn't be drawing it over here. You won't be able to see the upper part of it. Okay, let's erase a little bit. Let's draw it over here. Okay, so this is the electrolyte. Let's say we have this, and it's going to be now cathode. Cathode is the negative end. So that's how the battery is supposed to be. And this is the positive end. So the electrolyte must be a solution of salt of metal M. Let's suppose we wanted to electroplate it with gold. So it would be, let's say, gold chloride solution. Okay. And the anode is made up of strip of metal M. So this would be made up of gold. So we have gold anode, gold chloride solution, and the watch as cathode. As soon as we turn on the battery, this watch would be electroplated with a very thin layer of gold around it. I don't have exactly the golden color, but I can draw it with orange for your understanding, a very thin layer around it. The more time we're going to keep it in, the thicker this layer is going to be. Point one. Point two. This should be completely dipped, or at least the parts which we want to electroplate should be dipped. If there is some part outside, let's say this is the liquid level, then these parts are not going to be electroplated. Then you can safely raise these parts. That's how it goes. So be very vigilant with the diagrams. The theory questions have asked these a couple of times in the past 10 years. So this kind of question has been rare in theory and in practical papers. ATP I'm talking about, this is important for both paper 4 and paper 6, as this has happened in past. Okay. So I hope you get the whole point. Now what happens as a part of background chemistry, gold moves from here to here as gold ions. And since there are already some gold ions present in the system, they get attracted to this electrode. Gold ions are positively charged. They're going to get they're going to get attracted by the negative electrode. Since positive attracts negative, negative attracts positive. Simplest explanation. Important point. By the end of experiment, what would happen? Now, by the start of experiment, before anode looks like this, after anode might look like this. The anode gets dissolved. So this is the before and after for anode. This is the before and after for cathode. Of course, this is the before of cathode, and this is the after diagram of cathode. Again, one more thing. Before and after concentration of electrolyte remains constant. Make sure you note down that stuff. All of this that I'm explaining right now has been a part of past paper questions. And to be honest, this goes for all three papers. The stuff that I've written in this golden orange color is has been used in all three papers. Okay. So before anode is thick and looks like the whole plate or looks like the whole column that we can dip, but afterwards you'll find it dissolved. Cathode patterns up after at the end of the experiment, or at least there is a thin layer deposited. The more time it is going to stay inside the system, the thicker the layer is going to be. And before and after, the concentration of electrolyte remains the same. Why? Because if there are some gold ions that get refracted or electroplated on the cathode, there are some gold ions that are coming from the anode. So this stays balanced. Make sense?
Yes, sir.
What about you, Wes? You get the point? Wes, you there? Okay, I'm gonna assume that you got the point. So let's move on. If you have any questions, you may ask anytime. Okay, so
Sir, were you asking me?
yeah, of course, you're the only Wes here.
No, sir. My internet went away, and I got disconnected, so that's why I
Oh,
wasn't able to hear you.
okay.
So yeah, I have no questions right now.
Okay, good. Even if you have any questions when you go through the recording, you're most welcome to ask. Okay, getting back to it. So these are the questions that are all a part of electroplating, paper 2, paper 4, paper 6. Okay, the most important of the stuff for aqueous solutions has been given in this table or in this table right here. Then next, if we continue, if we look at the electrode reactions, then there is oxidation of usually non-metal ions taking place at anode. The exception over here is hydrogen. That's the exception because hydrogen tends to go to cathode, not anode. That's why metal or hydrogen ions have been written for cathode. All right. And they're getting reduced. So oxidation reduction is happening as a part of electrolysis. So this is pretty simple. You are always going to straight up explain that oxidation always happens at anode, reduction always happens at cathode. That's how easy it is. Just memorize it, and it's going to be the same every single time at your level. All right? So, moving forward, electrolytes for concentrated hydrochloric acid and dilute or very dilute hydrochloric acids have been explained over here. That's pretty easy since chlorine and hydroxide ions are always compete against concentration. So when it's concentrated, we have a lot of chloride ions. That's why chlorine is the product at anode. But when it's dilute, that means a little amount of acid and a huge amount of water, there would be a good number of hydroxide ions. They're going to win. They're always going to go to anode to form oxygen gas as a product. That's what's happening. On the other hand, for product at cathode, since there are only one kind of positive ions in here, that is hydrogen. Let me tell you, HCl gives us hydrogen ions as positive ions, and water also gives us hydrogen ions as positive ions. So there is no other negative or positive ion in the system. Since there is only one positive ion in the system, you always get hydrogen at cathode. There are no other ions to compete with. Easy enough? Let's move further to the last topic. Refining of copper by electrolysis. So it's more like electroplating. What do? We have the cathode, we have the anode, we have the whole system made up. And this is pretty much the before and after diagram of the same electroplating system that I've discussed. So we use copper to form both the cathode and the anode. It's just that we take impure copper as anode and pure copper as cathode. As soon as we turn on the battery, some of the copper goes over from the anode into the solution, and from the solution, they actually try to deposit on this cathode. Take a look, cathode has flattened. It's not of the same width as it was before. Take a look, anode has dissolved away. But since anode was impure, it gives away some sludge, some mud. It is also known as anode mud, and it settles down at the bottom. Whether you call it anode sludge or anode mud, it means the same thing. It has earthy particles like the soil, like sand, like silt, but it sometimes also has some very precious metals. So this material or anode actually contains precious metals, sometimes gold, sometimes silver, sometimes platinum. So we don't throw away this sludge. Instead, this sludge is further purified and the important materials are sold. A very good idea. So we keep replacing the anodes after regular intervals, and that's how we purify copper. Why do we purify copper with electrolysis, although copper is so less reactive? Why? Because copper is used in electrical wiring, and we need this kind of purity for electrical wiring. Imagine, this kind of purity is not something we're going to get with simple mining copper out of the earth's crust. So that's why we go with electrolysis. Although that is an expensive method, but that gives us the maximum purity of copper that we require. And this is really a very high level. The last level after it is 100% purity. And let me tell you, nothing is 100% pure in this world, right? 100% purity is just a hypothetical concept. We can't exactly reach it. There are always, though, no matter how small amount of impurities there are always impurities. So if we can get this high, that is good enough, right? And this actually completes our chapter. All 4 or 5 important points that we needed to complete today, we're done with those. Any questions?